Hello friends, welcome to Electronic Circuit Hub. So today we are going to understand about the thermal aspect of the semiconductor components. So we use lots of semiconductor components in our design. So it is very important to understand the thermal aspect of the semiconductor components and how you're gonna design the thermal aspect of your semiconductor components. So let us understand with the basic with the diodes. Okay, the basic with the diodes. So let's say you have the diode here. This is very simple, and diode is two terminal, as you know. And let us say at this point you have the tj of the diode. If I say the tj, that means the junction temperature of the diode. And here down somewhere, let's say you have the ta, that is ta is ambient temperature. So if you talk about the thermal aspect, that means thermal aspect means heat energy flow. Okay, heat energy flow, and which is in terms of p loss. If you know about the power loss of your semiconductor components, that is nothing but p loss is nothing but the heat energy flow through your semiconductor components. Now what you do, if you integrate this p loss to area under curve into dt, what does it mean? It means that the energy removed heat energy removed. Okay, so if you draw the equivalent circuit of the thermal aspect, so let's say here you have the p loss. Okay, let me draw this as a p loss. This is ambient, and here you have the tj. This is called the junction temperature. This here you have the ta, ambient temperature. Now you have somewhere here the thermal resistance, and in the thermal aspect you call this as a r theta ja. And then again you have the ambient, okay, ta. And if you compare with thermal, if you compare your thermal design with electrical analogy, let us draw the electrical equivalent circuit of this thermal aspect. So in the electrical equivalent, you have simple, this is your voltage source, plus and minus, and let's say this is ground, and then you have one resistance. Okay, and then you have, this is also going to be ground, right? So this is voltage source, this is resistance R, and current flowing through this resistance is I. So if you want to understand about, I would write the thermal electrical analogy. Electrical analogy. Okay, so what is the thermal electrical analogy? That means you're trying to understand your electrical design in terms of your thermal design. That is how, let us understand what is there in the thermal aspect and what is there in the electrical aspect. So it is very important to understand about this, your thermal aspect as well as your electrical aspect. So I would write here is electrical, and this is your then thermal. This side is your thermal. So in electrical potential I called is a ep, is given in the volt. Okay, if you look at here, electrical potential is given in the volt, while in the thermal, your thermal potential, let me write is for thermal potential is given in the T. And what is T? T could be in degree centigrade, or it could be in degree Kelvin. Okay, this is your T. This is your first point. Now let's talk about the I. Okay, so in the electrical context, your current is I. Your current is I. Okay, but if you talk about the thermal, it says about the power. This is your P loss. Okay, this is your P loss. So in thermal, it talks about the P loss. And what is P loss? P loss in what? We know the P loss. Heat dissipation across the semiconductor components. That is given by the P loss. Now the third point is, what is your R in electrical? R equals to V divided by I, and it is in ohm. This is in ampere. This is in volt. Okay. And what is in thermal? It is given by R theta Ja, and R theta Ja is given by T divided by what is your electrical potential in the terms of thermal. It is given by thermal potential, and it is T divided by, and what is your current in thermal? It is given by the T divided by thermal potential divided by the power loss. And what is T divided by temperature divided by power loss? This is your power loss. Okay, T divided by LOSS, power loss. And if you know that your T is in degree centigrade and your power loss in watt, so your thermal resistance in thermal aspect is given by thermal potential, that is T, or you can say also say the delta T. T are the delta T, I would say delta T divided by the P loss. This is your thermal potential, which you can define in the terms of delta T divided by P loss. And it is given by in degree centigrade, or else you can say it is given by in degree per Kelvin. Okay, so now if you understand the analogy, electrical thermal analogy, it's very simple. If you compare these two circuits here, so in electrical potential is given by volt, if you see here, while in the same thing the thermal potential is given by the T or delta T. Okay, the electrical current is given by I, and while we have the power loss in the watt, okay, W, and your resistance then given by V divided by I by Ohm's law here, and it is in ohm, while the thermal resistance is given by delta T divided by P loss, and wherein your delta T is in degree centigrade, P loss in watt. And what you can see, the unit of R theta J equals to delta T divided by P loss, and which is given by degree centigrade per watt or Kelvin per watt. So I hope guys you have understood what is the thermal aspect of your semiconductor components, how you're gonna design your thermal aspect if you're choosing any semiconductor components, if you're talking about the diode, starting from the diode and the BJT and the MOSFET, any of the semiconductor, if you are using in your design, it is very important to understand the thermal aspect of your semiconductor components, and how you're gonna understand the thermal electrical analogy. And if I say the electrical analogy, what is the electrical potential, and what you can write in the thermal aspect, and what is the current in electrical, what is the power, what you can replace the current in the thermal with the power loss, and you can replace the resistance in thermal with the R theta J junction to ambient resistance. And that is how you can understand the thermal aspect of your semiconductor components. Still, if you have any question on this, feel free to ask me in comment section.